Well, first of all, thank you, Ani, for the invitation, for the team that made this possible. It's a pleasure to be here. I have a number of connections now with folks here at Johns Hopkins. It's been great to learn about what people are doing here. The conversations I've had with Alex and others in the IDEAS team are very, very enlightening and kind of important as we shape similar efforts in Berkeley. This is all kind of uncharted waters for many of us, and so it's very useful to trade battle notes on what works and what doesn't on this kind of work. So first of all, by California state law, I have to disclose my connections to companies that are supporting my work or that I have a financial affiliation with in one form or another. But I want to kind of get to the meat of why we built the tools that we're building and kind of what our focus is. My background, my training in this horrible place called Boulder, where I got my PhD, that is boring and doesn't have pretty mountains and has no climbing, was in particle physics, in lattice QCD, for those in the audience who may be physicists. And this was a quote that I saw posted on the door of one of the faculty in our research group that it comes from a classic book in numerical analysis from Hamming from the 60s, but if that was true in 1962 and Hamming was concerned about that, obviously today, when we have more compute power in our pockets that Hamming could ever dream of in 1962, that is ever more true. And so what we're trying to build are tools really to help humans think about what they're doing while they're computing and to take that process of thinking into the world of science as a human enterprise. So we are sort of we try to position ourselves as the bridge between the humans and the algorithms and the tools and the data and the code and the computation. And part of that comes from kind of thinking about this very cartoonish description of what we do as computational scientists. And I know that this is highly oversimplified, but I don't think it's completely inaccurate that these stages are part of what we do in computational research. We play with ideas, we try to collaborate, and often that means, or it used to mean, emailing back and forth. People would email their scripts back and forth, and then, we got to rewrite the prototype so it runs in production at scale in some other language, and then if we're going to publish something, people would copy and paste all of their results into the manuscript, and God forbid reviewer number 3 asks for a change of parameters or asks a question about something, because now 6 months have gone by and nobody knows how that figure was produced, right? And you go spelunking and calling the postdoc who's now hiking in Vietnam in the jungle and you can't get a hold of them. And if you're lucky and you survive through all that, you get to teach your students by copy-pasting again now into your PowerPoints, and they can't look at your data, they can't reproduce what you've done. So how about we think that this is just one problem, not a sequence of problems, but just one problem of thinking about the life cycle of research ideas as a single question, and where we should be able to move back and forth fluidly in that spectrum. And I'm not saying that we have all the answers, but I think we can build partial solutions to this. And it honestly starts from very simple and very old ideas. And it goes back to an acronym that I haven't actually traced in the literature where it was first introduced, but the acronym of the REPL, the read, eval, print loop, which is the Unix command line or the terminal command line, environments, scientific computing environments like MATLAB, or in this building probably more IDL than MATLAB. I cut my teeth on IDL myself, Mathematica and others, right? Systems that read our input, do something with it, give us back something to look at, and keep waiting for us to type. That really is kind of the very simple tool that we've all used. And I think that tool is important, and I like Legos, but I like these Legos. I don't like these Legos so much, because as a scientist, I never know what my problem is going to be next. I'm always exploring, and what these Legos give me is a vocabulary in which I can build up the next question. I can look at what happens and then I can iterate, right? And that really is what interactive computing means for us, right? It is tools where we express what we're doing and we have a dialogue with the machine where we look at the result, we look at an answer, and that informs the next thing we do in an iterative process. The pre-molded Legos where you can only build the 1 or 2 things that are printed in the box, and they look really shiny and pretty and they're all curved and whatnot and they look like what was in the movie, those are the GUIs that basically force you into one workflow, that make it very difficult to recompose ideas in a different way, to abstract what you're doing, to record in a reproducible fashion for others to share what has happened. And so I kind of like simple things, and it's also easier for limited brains to think about simple things that can be assembled. Things started actually quite simply. I was a grad student faced with, you can argue that I was faced with the threat of having to actually graduate and finish a dissertation, but also with the more technically important and relevant problem of having too many tools and too many languages hopping around in my simulations and analysis, and it was Perl and Bash and awk and GNU-Plut and IDL and C, and I literally had a stack of books on my desk. And so somebody told me, hey, you should learn about Python. It's a cool language, and you can use it interactively, and it actually does a lot of what these tools do, but in a simpler fashion. So instead of writing my dissertation, I sort of disappeared for a few weeks from my advisor's radar. And at the beginning, IPython was just an enhanced interactive shell. So it was just a REPL. It was a very simple idea. Give me a REPL, but give me a REPL where I can do what I need to do as a scientist, which is not just type Python code, but actually run a script and see a meaningful error message that is well formatted while I have 5 plots open, and while I type ls and I access my file system, and while I just conduct kind of the daily business of a scientist using a computer, which is different from the daily business of a software engineer building software that has a well-scoped and advanced goal, and where the point is having a good IDE and all of the good tools of software engineering. So we're not trying to replace that, and we're not saying that scientists are full-time software engineers, but we are saying that scientists use computers and they use programming languages to understand problems. And so this is what we were trying to build. That effort, which I told my advisor would just take an afternoon, started as a 260-line Python script, which you can find on GitHub. And it basically loaded the very basics, a little bit of interactive workflow, GNU-Plot integration, and preloading what was called numeric at the time, the Python numerical library. Today, it's a monstrosity. We span multiple GitHub organizations, over 100 repos, over 500 contributors. We estimate order 3-4 million users with a naive model that I can defend, but that is probably an undercount. In direct funding, we've had about $8 million in funding, so it's not really a lemonade stand anymore. And it's a collection of people who do all the hard work. So it's not me. At this point, I started something 15 years ago, but I cannot, everything you're going to see now is really the credit of an amazing team of people. This was a picture from our last all-hands project development meeting in the spring, and there are people here from academia, like Brian Granger, who's a professor in physics at Cal Poly in San Luis Obispo, and who has been kind of my main partner in driving the funding and the project for the last 10 years or so. But we have people from industry, such as 2 mathematicians from Bloomberg. We have people from national laboratories, Shreyas. We have people from Continuum Analytics in industry. We have people from Google, people from IBM, graduate students from Berkeley. So we have a collection of people from a variety of academic, government research, and industry research who all participate in this project kind of on an equal footing. These are the people who have funded us, and up until recently there were no federal agencies in this picture. We owe an enormous debt of gratitude to the Sloan Foundation initially, who funded us, and then the Moore and the Helmsley Foundations, the Helmsley Trust and the Gordon and Betty Moore Foundation, as well as the Simons Foundation. Private agencies have been really the main sources of resources for us. I just got a grant from the DOE, so if anyone here happens to be interested in a postdoc position on interactive kind of computing in the context of high-performance computing workflows and kind of large-scale HPC data analysis, come and talk to me at the end, because I'm looking for a postdoc right now. And now, as I mentioned, we do have very, very strong partnerships with industry as well. I also want to flag that our project doesn't exist in a vacuum. And so back in 2012, Perry Greenfield and 2 other people from the scientific Python world, Travis Oliphant and Jared Millman, and John Hunter, who was already mentioned by Annie, who was the creator of Matplotlib, we got together and we created a foundation called NumFocus, which is a 501c3 that provides a fiscal umbrella and a legal infrastructure for open source projects that are in the scientific space. And this is actually the legal home of Jupyter. The legal home of the project of IPython/Jupyter is not LBL, it's not UC Berkeley, it's not Cal Poly San Luis Obispo. It's a neutral entity that gives us a bridge between academic research, government research, industry, as a nonprofit for the public good. The 5 founders were, as I mentioned, people who came from the Python community, but it's not a Python-specific project. There are projects from the R world here. There are projects from the Julia world. There are language-agnostic projects such as software and data carpentry that are really about training and education in data science and software for scientific computing. And John Hunter, sadly, as we were founding NumFocus, passed away, which was a big blow, especially for some of us like Perry and I who were close friends with John. But the foundation has really become one of the anchors of sustainability for these open source efforts that tend to flow a little bit in between spaces. And I know how many people here have any connection with the Space Telescope and the AstroPi project? Okay, so quite a few of you. I read the paper about the AstroPi. I didn't read the paper, but I read the abstract and I have it downloaded because it came out as I was coming here. There was a paper about the AstroPi problem, the funding, how to fund sustainably projects such as AstroPi. And obviously AstroPi is a project within NumFocus. This is a hard problem. I'm not saying that NumFocus has a solution, but it is an entity that tries to help on this problem, and you can talk with Perry and myself and others about it. So, getting back to the technical questions, on the tooling side, we started with this very simple thing, basically a REPL, and then it really was a matter of trying to generalize and abstract that idea and see how far we could push that idea of a human interacting with a computer to do useful things. And around 2010, Brian and I got together, and in a little mini marathon of coding, we actually took the basic idea of what happens when you work interactively, and we ripped it out into a proper server, a proper client process, and a proper protocol with a well-defined messaging specification. And at the beginning, it was a small toy, 2 Python processes and a file declaring what the messaging spec was. But that idea of separating those two things was basically the starting abstraction for building an entire architecture that, as I hope I will show, has carried quite far. The first thing we did once we had that separation between the process that originally was just like a terminal, like a shell at the terminal, was to build a graphical, in collaboration with a company called Enthought in Austin. We built a graphical terminal. This looks like a terminal, but it's actually a Qt graphical application where you can have multi-line editing, you can have syntax highlighting, you can have embedded inline plots. It turns out that real terminals can pretty much do that now. But this was not true 5 or 6 years ago. Like the modern terminal emulators are starting to get to this. Now we do have syntax highlighting in a normal terminal, thanks to a new tool as of IPython 5. And with a couple of tricks in some of the terminal emulators, you can actually display inline images. But this was not possible 5 years ago in a normal terminal. It required a dedicated app. But the point of that was really to show that you could have an environment where you could have code and richer output than what you would normally have at a terminal. And the real goal that we were after, and I'm not claiming to have that we invented this, was really a notebook environment. Several of us in the project came from a physics background, and we had used heavily systems like Maple and Mathematica, which many of you probably are familiar with. Those systems have had notebooks for a long time. It's just a very natural environment to work with. For those of you who haven't, who here has not seen IPython or Jupyter notebooks before? Okay, so for those of you who haven't seen them, this is what they look like. And so a notebook is a document, right? A document that can contain text in English and in human natural language. That text can include mathematics. You type LaTeX in between $signs and it gets rendered. But it can also contain code. And the code can produce output. And it's basically that. So to first approximation, you can think of this as Google Docs with a brain, if you will. Because you have a document and it's accessed, if you see the screenshot, that's a web browser, that's my Chrome web browser. So you're accessing computation through the web browser, kind of like in Google Docs, but in addition to writing a document, you can type code in a programming language, and this uses this idea that there's a kernel and a server, and so you send code for this kernel to execute, and the process executes it and sends it back to you, and you have the results. And the paradigm that this produces is what I'd like to call literate computing. For anyone who has a CS, kind of is familiar with CS lingo, Don Knuth, the creator of LaTeX, of tech, in the 70s introduced the concept of literate programming, which is this notion of writing programs, writing algorithms, writing software as a single document where you combine human language and source code, and then you run that document through a process that will either produce a program, a binary that to be executed, compiles the source code into a binary, or compiles documentation, takes the human language and builds an annotated version of the documentation, right? So literate programming is a well-established paradigm. There's a lot of CS literature on it. The emphasis here is different because, as I said earlier, the use of computing that scientists make is not exactly about writing big programs that have a very well-defined goal. It's about using the computation, using the programming language to understand a question, to understand a data set. It's often very specific, whereas computer science and the goal of the kind of thinking that Knuth is after is generalization and abstraction as much as possible. Often the use of computers by scientists is the opposite. It's actually in understanding this one data set, this one problem as well. Now, that may be the basis of the formation of new theory. It may be the basis of new generalization. But the usage of the tool is often a very specific one. So I prefer to call it literate computing because it's about using the computation and the narrative about this problem, and it's about live computing. So it's kind of an inside-out version of those ideas. Now, I've been talking about IPython because the project was born as a shell for the Python programming language. We call it the IPython notebook. But once you have made these separations, once you've cut things out, it turns out that you can generalize, because I was just talking about how the tools are often used for one problem, but we're not afraid of generalizing when it's appropriate. And what happened was, we started looking at what we were doing with this tool. I've shown you the interactive Python shell. I've talked about how we have a kernel for this protocol, but I've also shown you this graphical console. I've shown you the web notebook. It turns out that there's a bunch of other tools for managing these notebooks. It turns out that these parts of the project are very specific to one programming language, the Python programming language. But a lot of these things, ultimately, who cares what code is in that box? As long as somebody understands that code and can give you a result back or print a picture back, who cares if it's Python or IDL or MATLAB or R or Julia? And we began generalizing and basically making the programming language simply a parameter in the protocol, so that you can say, this is going to be talking this language, and that's it. But once that happened, people started saying, well, I'm very happy to have that, but I don't want to run my Julia system called IPython. I don't want to run my R system called IPython. Could you call it something else, please? So that's what became Jupyter. So Jupyter was really a name that is inspired by Julia, Python, and R. They're the three open languages of data science. It's not an acronym because we have many more programming languages in the system, but it's inspired by those three. And if we think about kind of what are the fundamental ideas behind it, it's useful to think about how the web works. The web is basically built around sort of two big pieces. One is a protocol called HTTP, and one is a format, a markup language called HTML. The protocol allows things to talk to servers, right? Typically, those things are web browsers that talk to HTTP servers, but they don't need to. You can actually build things that talk to HTTP where you don't have a web browser in front. You can build a REST API over HTTP to talk to your database, to talk to your computational services without having a web browser in the process. That's the point of being a protocol. Once you specify what the protocol is, anyone can talk to the protocol. The server can change and the client can change. Now, if you want to encode that content in a format that is meant to be rendered for human consumption, then you do encode content in HTML, and that content can be rendered by this specific tool. And we sort of have the same thing. We have this protocol that I've talked about where a kernel executes code and receives messages, and the protocol is implemented as a combination of, we use a networking library called ZeroMQ that provides very specific communication patterns and sockets. It's written in C++, and it has bindings for just about every language out there, which means anyone that has access to bindings for that library can implement the protocol. And then the data that travels over the protocol, the messaging specification, are JSON packets, which means if you want to speak this protocol, you need ZeroMQ bindings and you need a JSON encoder. And today, that's true for almost any language you can find out there, which means it's possible to implement this for almost any language. And then we have these notebooks, which have a document format, right? Kind of like HTML, we have a document format. That format is actually on disk. It's actually JSON. It's a data structure with lots of metadata, so you can do other interesting things with it. The protocol is basically the REPL idea on steroids, right? We're going to be sending things back, but now we're working, it's not 1971 anymore. So instead of saying print, it's print on steroids. Print can be text, but it can be show me an image. Basically, any MIME-tout output, anything that a web browser can represent, it can be LaTeX, so that if you produce mathematical output, we actually understand it and represent it as a first-class object. It can be HTML, so that you get nice kind of modern representations of your data on the web browser. It can even be interactive JavaScript. So if you want to do parameter exploration over a specific parameter for something small, you can say, oh, give me this just one little bit of code, and then that automatically builds a small local graphical interface that allows you to control parameters. This is something that we understand as a type, as a kind of output, because we basically said, let's imagine what the 1970s REPL should look like if it was 2015 or 2011, and we had the modern web as the environment where we operate. Because the protocol is language agnostic, as I mentioned, it supports beyond Python and the IPython kernel. It supports Julia, it supports R, but it also supports a gaggle of other languages. Last time I checked, there were about 75 implementations of the protocol for different programming languages of various levels of quality. That list of 75 is a wiki page where anybody can add a link to their kernel. So some of them are production, kind of battle-tested production tools. Some of them are an afternoon project to kind of test in some toy programming language the idea. But the point is it's an open protocol and anyone can implement it. As I mentioned, a lot of our intent is to build these as tools for scientists. And one important concern in science, and I think something that is becoming increasingly a matter of concern, at least for many of us in the scientific community, is the issue of reproducibility in scientific research. And I want to start with a quote that some of you may have seen if you've read some of the literature on reproducible research from David Donahoe. David Donahoe is a statistician at Stanford, very well-known statistician at Stanford. And he developed a toolkit for signal processing with wavelets. I want to highlight the date on that quote. This is from 20 years ago, right? And I think Donahoe's idea from 1995 is something that I very much subscribe to, that today we should not be in the business of calling research just the publications that get people the cover of Nature. I mean, it's great that that happens, but that's not where the real work goes, okay? The real work is the stuff that's behind the scenes. It's the stuff that if you read the paper that made the cover of Nature, chances are, if that's all the authors give you, you will not be able to build upon that work by yourself, because it would probably, even if, let's assume the data was public, because it would probably take you way too much effort, there's way too much work to get to that point. And so, here's an example of a paper from Nature Genetics. I can't speak to the scientific quality of the paper because I'm not a specialist in head and neck cancer, but let's assume for the sake of argument that it is a solid paper in head and cancer research. And there's one reason why I am willing to at least give these authors the benefit of the doubt that it's solid science. And it's not because it's in Nature, by the way. Highest impact factor journals are the journals with the highest retraction rates. It's because the authors did this. When they published a paper, their supplementary material is linked to a GitHub repository that contains not one, but 20 notebooks. And those 20 notebooks, step by step, in excruciating detail and with lots of annotations, take you through the entire process of producing every plot, every table, every figure, every result that they cite in the paper. And a lot more, obviously, because the paper, Nature page limits are that big, and so they had to pick and choose the few highlight plots that they wanted to include. This has everything. That makes me think, as I said, I'm not an expert, this is not approved, but that gives me confidence that these authors are serious enough to share their entire analysis protocol starting from the data, that the work they're doing is probably at least solid and it's been through public scrutiny. And this, I think, is exactly an embodiment of what David Donahoe proclaimed we should be doing 20 years ago, and now it's possible. Now, if we really want to make the whole thing end-to-end kind of plug and play, in 2012, we gave a first demonstration of some of how this could be done. This is a paper that, in a collaboration, I'm not a microbiologist, but in a collaboration between our team and a set of microbial ecologists at the University of Colorado. Now the lead author on this, Rob Knight, is now at UCSD. We did some work on analyzing some of their data from basically the structure of assemblies and gene sequencing reads by moving it over to the cloud and parallelizing it using some of the IPython parallel tools. And in addition to publishing the results of how this process was done and some of the biological conclusions, we published not only the notebooks behind the work, but we actually published, and obviously I don't expect you to read here, but this is a companion web page where the important point is that down here, there's an Amazon machine image code. There's the identifier of the Amazon virtual machine that we used to run the paper. And so if you copy this config file into your Amazon, this was using something called Star Cluster, but if you can just do it by hand by going to the web console and say, boot me up this machine, you're effectively booted into the paper. So you're live running in the paper. It's up to you to decide whether you want to run the paper, because the full analysis would need about 24 hours of execution of a reasonably large Amazon cluster. It would cost a few $100s. It's not a fortune, but it's real money. So we included a subsampled version of the data that would run on the cheapest, smallest Amazon machine you could boot up in about an hour, so it would be like the cost of a cup of coffee. The idea being, you can actually, for the cost of a cup of coffee, run the real analysis, granted with the caveat that it's a subsample data set, and validate the results. And then if you decide that you want to do it for real, if this happens to be your real research, before you spend even a few weeks worth of anyone in your lab's time, spending $300 to run the full validation is actually cheap insurance. And then you're starting from the real code and the real data, and you can build something else. Now, doing this in 2012 was kind of a proof of concept. It was clunky. You had to know a fair amount about Amazon infrastructure to do it and build the AMIs right and whatnot. Up the street, well, a little bit up the street from you folks, Genelia Farm, which I understand is with good traffic, not much more than an hour from here. Jeremy Freeman is a neuroscientist who works there. He runs his lab there. And what Jeremy and his team did was say, well, if you give me a GitHub repository that has all of these notebooks already, like the ones that we've been talking about, and you also tell me what are the runtime dependencies that this code assumes it needs, right? If you give me in a standardized format what other things it needs, I can clone that repository, I can grab those dependencies, I can compile all of that and give you the URL to a Docker instance running in the cloud, and he's even willing to pay for it out of his pocket from his own grants, so that instead of giving you simply a URL to look at a notebook, you get a URL to boot into it, courtesy of his grants, and you can execute the code right away. So now, this entire notion that David Donahoe was talking about as an idea in 1995 is literally one URL, like paste the name of a repo and click submit, and you're done. And this is being used for real. So we've been talking about microbes, but to come to the kind of context that this building was built for, a very long time ago, in a galaxy far away, two black holes decided to spiral into each other. They were close enough that they started spiraling into one another, and in 1915, just about 100 years ago exactly, Einstein predicted, when he wrote down the field equations for general relativity. For those of you who are not physicists, this is if I remember correctly, that's the curvature tensor, the Ricci tensor for the field equations. Predicted that if something like this were to happen, if two very massive objects began moving in a really fast manner through space-time, they would distort space-time itself in a way that would generate waves, and those waves would travel through space at the speed of light, and we should be able to detect them because they're waves, just like this light is a wave, except that instead of being the vibration of an electromagnetic field in space-time, it is a vibration of the structure of the space-time continuum itself. The problem was detecting those things is highly non-trivial. So a long time ago, I think it was in the late 60s, early 70s, was when Thorne and collaborators proposed the original idea of how to detect these things. They proposed that if one were to build two interferometers, two laser interferometers, for those of you who are not, I imagine not everyone here is either a physicist or an astronomer. So an interferometer is an instrument that has two arms at 90 degrees, and you shine at where the two arms meet. You have a laser in the middle and a beam splitter that sends light down both arms, and there's mirrors at the end, and the light comes back. And if the arms are of the same length, those two paths are identical, and so light goes up and comes back down exactly in phase because you're sending coherent light, laser light like this. And so they come back in phase, but if there's any, even a very minute difference in length between those two arms, those paths are off, and because light has a very, compared to macroscopic distances, light has a very short wavelength, that shift in distance will immediately induce a dephasing between the two beams, and you will be able to detect that. So it's basically a very, very sensitive instrument to detect changes in length. And so you imagine if a gravitational wave goes by, one of these arms is going to change in length relative to the other, and you should be able to detect that. There's a small problem. For those of you who are not instrumentalists, 10 to the 21 as an instrumental signal-to-noise constraint is really, really nasty. To give you an idea, to put it in imaging terms, Imagine you're looking in an image for an object of roughly the size, say, of a human being, like order of magnitude 1 meter. But the image you're looking into is not an image of the size of this room. It's not an image of the size of the city of Baltimore. It's not an image of the size of the Earth. It's an image of the size of the Milky Way. That's roughly what 21 orders of magnitude means. Looking for a 1 meter object in the entire galaxy of the Milky Way. So it took them a pretty long time to make this work, but phenomenally they did. So the reason there's 2 of these instruments is simply that you have to disentangle every other possible imaginable source of noise. And one of the things that you can use for that is having 2 faraway instruments. So because anybody walking down the hall in Louisiana waves in the ocean a few tens of miles away, somebody drops a hammer in the building next door, anything like that causes a signal bigger than the thing you're looking for. But that signal is not going to be replicated between Hanford, Washington, and Louisiana, right? And so that is one of the tricks they use, in addition to unending amounts of thermal isolation, vibrational isolation, and then ridiculous amounts of statistical and signal processing after the fact. Point is, they did it. And in September 14, 2015, technically 3 days before the instrument went online, so the instrument was in final engineering testing, and in fact that night they were going to run a series of tests that would have made it impossible to see the signal, but it was getting late and they decided, we'll do it tomorrow. This signal arrived in Washington, and this was the signal, the Washington signal overlaid on top of the Louisiana signal. Basically, perfect coincidence. The row below are the numerical relativity simulations of what 2 black holes of those masses would look like. Obviously, they fitted it over the masses and whatnot. This is the best fit simulation, but the point is, the residual between the experimental signal and the numerical simulation is very, very small. This is a spectrogram of the signal. So this was discovered. It's probably going to be one of the most cited papers and figures in physics for a few years to come. All of this was done using matplotlib, so it is also a victory for this kind of open source work that began 15 years ago when we were kind of a few crazy loonies screaming in the desert. It turns out that actually all of this was done with open source, reproducible tools using matplotlib, and the LIGO team at their Open Science Center publishes now this analysis. If you want to replicate all of the analysis of the data, starting from the raw data, look at how the denoising works, et cetera, you can go to the LIGO Open Science Center and download it as a Jupyter notebook. And as I mentioned, remember we talked about representing types of data. There might have been audio here if I had asked for it. Oh, here we go. Maybe this will work. No, this is not going to work, so let's try just the old-fashioned way. So remember I said in Jupyter we talked about representing computational outputs of whatever kind. Well, if you take a waveform, you can sonify it, right? Instead of, this is the time series, the time domain representation, this is the frequency domain representation, and that little whoop, that is the sound that 2 black holes colliding 1.3 billion light years away make in the dark of night. That's the sound, the song of the universe. And now the LIGO team, so they published that, and we actually sent them an email and said, hey folks, you can make this available not just in notebooks for people to read, you can make it available for them to run with this binder trick from Jeremy's lab. And so now they actually do that. So if you now go to the LIGO Open Science Center, the new data releases actually come out of the box with a binder link for you to run, and now they're actually wrapping them not only to run on Binder, but to run on the Microsoft hosted version. So Microsoft has a hosted version called notebooks.azure.com, where you can get notebook hosting for free with execution. I mean, the free account gives you up to a limit. And the LIGO team actually puts up, they put up the data releases in ready-to-execute notebook format on their webpage. So it is possible to use these things for major research and to make major significant kind of history-making research open to the public. It's also useful to work in this manner for little things. So this is an anecdote from a recent trip a few weeks ago to Boulder, I was about to get on a plane to go give a talk at CU Boulder, and I caught a rather flashy press release from the MIT Tech Review about a paper, and I don't want to focus on the claims that this paper makes about deep learning and physics and Hamiltonians and the nature of statistics in the world, but there was an interesting result. It's a paper from Lin and Tegmark at MIT and Harvard. There was an interesting result that caught my eye. There was a theorem in the paper that said that if you build a deep learning style network with the simplest network that you can think of, and so it's a neural network that has a single hidden layer, just one hidden layer, and very importantly, it's a hidden layer with only 4 nodes. This very simple neural net that has a standard sigmoid nonlinearity attached to it can approximate to arbitrary precision the multiplication of 2 numbers. So it's a single network that takes 2 inputs and produces 1 output. And if you take u and v, it'll multiply u times v. The point is, it's been known for a very long time that neural nets are effectively arbitrary precision interpolants and approximants for a wide variety of functions. We don't know exactly the class of functions they do that for, but all of those classical results were such that if you dial the accuracy constraints more tight, the size of the networks grow. What's interesting and what caught my eye, I don't know that literature very well, by the way. I actually had to ask on Twitter if this was a new result. But people say that it really isn't a result, and what's interesting is that the size of the network is fixed. And there's an important constant in here that comes in from the network. And I was like, well, I don't know this stuff, but this result sounds interesting, and I want to understand it. So let's try to implement it. I mean, I take Feynman's classic quote in the sense, create, meaning if I can build it, I'll understand it. So let's build it. So I started writing a notebook on the plane to kind of teach myself how this worked, and I actually asked, since I don't know any better, I asked on Twitter if this was actually a new result. People said yes. But as I did the work, and this is the kind of thing that that is what implementing that affine layer looks like in Python. It's 1 line of code. It's completely trivial. I ended up being off by a factor of 2. I had this weird thing where I could make it work, but to get the right answers, I had to put a factor of 2 somewhere that I couldn't figure out. And I went through the algebra several times. It didn't make sense. So I posted it on Twitter and put it up on GitHub. And within 5 hours, one of the authors of the paper was like, yup, we messed up. We were off by a factor of 2. They basically got caught up in a definition of their Taylor series. They absorbed the 1/2 that goes in front of the second derivative in the Taylor series. They absorbed it into their definition, and then they forgot about it later. And I read it, and I got caught in the same mistake. Completely trivial mistake. But the point is, this kind of working openly, sharing things, putting it up there is exactly, this is a completely trivial example. It was a couple of hours of just me teaching myself how to understand a paper while on a plane without the internet. But that actually is how we should be working, I think. So from big things that make nature and that are going to get people Nobel Prizes down to the little things that we do every day, I think this is a useful way to work. Now, an example of how these tools are being used to make the scientific literature more accessible is also books. So this is a book on Python for signal processing that was the first example of how you could give the readers the scientific literature in a way that was fully executable. Now there's been many other books. The most recent one from the same author, Jose Pinco, is a book on probability statistics and machine learning that also comes with a complete collection of notebooks for you to execute. I haven't had a chance to read it yet, but I just bought it last week. We did a demo showing the value of these things with nature a couple of years ago, where what we did was we took, on Nature, we posted a little website that was hosted on the Nature domain to demonstrate that it would be viable to do this actually within the constraints of a publisher. And we took an image. I've shown this talk before, but there's nowhere is it more satisfying than to be here to have that image, since that image came from here. It's one of the most iconic images in nature and in the history of science. And what we did was we put up that image together with a very, very simple bit of code in Python using the scikit image library for image processing, and a few parameters, these JavaScript little controls that I told you about, for you to interact with the galaxy, basically with image processing thresholding points to detect what would count as a galaxy in that image. Obviously, this is not a new scientific result. This image has been around for a long time, but the point was we wanted to show the public that a scientifically realistic and relevant piece of analysis could be presented on a major publication environment in a way that the public could interact with it, execute it, change the parameters, therefore question the assumptions of the authors, and build off of it. This has been adopted widely. There's now, if you go to GitHub and you check, there's over 500,000 notebooks hosted on GitHub, so it's something that has been widely adopted by the open community. And so what we have is sort of an environment where around these open standards, we have a space for the scientists to iterate, to absorb data from whatever sources it may come. There are people who have their data in CSV files. I know that a lot of the work that is done here is around structured databases, for example, for astronomical analysis. This place has been a pioneer in that kind of work. And then you produce outputs from that structure in whatever format makes sense for the audience, right? If the audience needs to read something online, you can publish online. If you want to produce a PDF, then you can actually convert these things to PDF or to a book or print them. But the object of record is this underlying rich metadata intensive data structure where you can do other things and you can kind of produce the outputs for humans or machines to consume as the needs dictate. So these foundations now are actually kind of adopted as infrastructure in many places. We have developed in the last few years something called Jupyter Hub that allows you to run the same environment in a multi-user context, therefore supporting many other use cases. At Berkeley, in 2015, Jess Hamrick, who was a grad student, had to teach a class, and faced with the prospect of doing, well, her advisor was teaching, she was a graduate teaching assistant, faced with the prospect of doing tech support for 220 students with installation, she said no. So what I'm going to do instead is build a very, very sophisticated and elaborate system to deploy this in the cloud so that all the students, all they need is a web browser and they can log in and do the classes. In addition, in collaboration with Brian Granger, they developed a system called NB Grader for managing notebooks as homework, to grade the homework and return it back to the students. And now UC Berkeley has adopted her original prototype and has put engineering staff behind using it as the platform where the new Berkeley Foundations of Data Science undergraduate curriculum is taught. So this is a course that is ultimately aimed at the entire undergraduate population at UC Berkeley. It's part of the new Educational Data Science Initiative at Berkeley. The course is open online. You can go to inferentialthinking.com and read the course. But as you're reading through the textbook, you'll see these blue buttons. If you click on those blue buttons and you have a Berkeley ID, you will be taken to the live hosted version of the textbook on that infrastructure. So, and it's plugged into the Berkeley authentication system so that students in the system knows if the student is registered or not, because it's also plugged into the class management APIs from campus, and it deploys things automatically in the cloud. So it now provides a multi-user system that can serve an entire university. That, by the way, I want to mention that Foundations of Data Science course, which is an introductory data science course for all of campus, is just the base layer, hence the name Foundation. And the way this undergraduate program is structured, there's a collection of what are called connector courses that now take this basic common course that teaches a little bit of programming and basic inferential thinking to students of any major on their freshman year, which means that you can't make assumptions about prerequisites. Now it takes those foundations and pushes them in the different directions that they may be interested, including all the way from computation, data structures, and statistics and mathematics to the more mathematically inclined, to things like smart cities or ethics for students like in the law program or in the humanities who may be interested in those questions. So this idea has been deployed in many other places. In educational contexts, Berkeley is not the only place. There's a bunch of universities that are using similar setups. Supercomputing centers are becoming very interested in using this as a tool to access supercomputing facilities. So NeuroSquare, which is right underneath my office at LBL, but also the supercomputing centers at various universities. CERN now provides to, anyone here work with the LHC? No particle physicists in the room? Oh yes, one person. So have you by chance used the CERN Jupyter installation at all? No? Okay, so I know that they've been developing a deployment. One of my postdocs visited there last year. They've been developing a deployment of Jupyter attached to the compute machinery at CERN and the data storage machinery for the CERN scientists to collaborate. The Wikimedia Foundation actually runs a deployment of Jupyter Hub in the Wikimedia cloud with access to all Wikipedia data. All you need to have is a Wikipedia account. So if you have a Wikipedia account, you can access that and use it to run Jupyter notebooks and with pretty good setup against all the Wikipedia data or all the data that is available in their research cloud. I don't use it myself, but I know it exists. Industry is picking it up. So this is an example of an educational project from O'Reilly, which developed a system called Oriole. And so O'Reilly earlier this year launched the system to allow you to take something like a notebook. So this is an example of a notebook written by Peter Norvig. Peter Norvig is the director of research at Google and is a well-known figure in the world of artificial intelligence. Peter blogs often in the form of notebooks where he takes a computational question and kind of decomposes it in these lovely annotated descriptive documents that kind of walk you step by step through his thinking process and the solution. And what O'Reilly built was a way of taking that into a regular website. It looks now like a normal web page. It still has areas where you can run the code and execute it, but then there's a video narrative, and the video narrative is automatically time locked to the reading flow of the document. So as you're reading, Peter is basically talking to you through the process. And if you go back, the video winds back. There was a seamless, basically live narrated version of the document, but you still can execute it and you can still change it. So in my mind, this is kind of a perfect integration between the human narration and the original kind of intent of the computational document. Now, a bunch of other companies have built commercial products. So Microsoft, IBM, and Google, and Continuum, they all have cloud-hosted versions of the system hosted on their servers. And in each of their cases, it probably ties to some of the services that they offer that are kind of unique and specific, like the Google Data APIs or the Azure Machine Learning Platform, et cetera. Because we've defined an architecture and a set of protocols, people can implement other things. So now there's an example of a project called Interact, which actually builds a native application. It's not a web-based application, it's a native desktop application for handling notebooks. It uses the same messaging protocols, it uses the same file format, but it provides for us a web-based delivery system for the kinds of use cases that I've explained, such as education, such as supercomputing centers. It's a very useful format, but sometimes you do want an alternate client, and there are other people building these things. And I want to close with some notes about where we're headed next. So our user base, as I said, we can kind of eyeball it at a few million users. It's hard with open source things that anybody can download, but we have models to back that up. IBM ran a user experience survey last year, and we sort of got information about what our population of users is. It was run for a while. It collected very good data. If you're interested not just in looking at the data, but in playing with it, with IBM, we've been developing, and this has been mostly their work, ways of taking a notebook and presenting it as a live dashboard where you can hide all the code and just look at the controls and just play with the data. And so this URL will give you basically the view of the notebook, but now there's no code, and what you have is just the controls to play with the data. And what we learned was that there were a number of needs around interactive coding beyond only developing notebooks, about flexibly laying out all the tools for computation and adding potentially tools like variable access or better debugging tools that were not quite met by the notebook. Now, if you look at what we call the notebook today, yes, you open this thing and you can have notebooks, but it also has a file browser, and it also has actually a terminal emulator built into it, and it also has a text editor, and it also has a process manager, and it also has a cluster manager. It's just that these things are glommed together in a very ad hoc way. So what we did was we said, well, let's take all these building blocks and imagine what should an architecture that takes all these things and puts them as equal class citizens and gives them ways to talk to each other on top of the underlying compute services that we have, what should that look like? And so we built what's called Jupyter Lab. Jupyter Lab is basically that scaffolding where you can put a notebook, you can put, this is not a notebook, this is like that graphical console I showed you earlier, but now it's a re-implementation of that inside of the browser where you're not building a document, you're just typing code and looking at results. So think of it like your permanent notes and your scratch paper. When I did my homework in physics, I would always have my big notes and a piece of scratch paper where I tested calculations out. This is your scratch paper. You can have your terminals. You can recompose these in a different layout. You can add new tools. This is a regular text editor if you're doing regular code development there. And because it's a plugin based architecture, new tools can be added. These tools that we've put in are kind of the basic ones that we already know we use and we need, but they're just plugins, and other tools can be added as plugins. And this is being developed in close collaboration between our team and teams in industry, Continuum and Bloomberg, and it's kind of interesting that there's a lot of buildings and things named Bloomberg around here. This has been a very productive partnership with Bloomberg, where several engineers at the company have actually been working in close collaboration with us, building this open source platform, and obviously they will then use it to develop whatever other projects they need. Our plan with this is that right now, it's sort of an early friends and family preview. It works, you can get it off of GitHub, but be prepared for stuff to break. Because everything is changing rapidly. But our plan is that over the next few months, we'll be kind of releasing it in alpha and beta modes while the same existing notebook is there available. You can begin testing it. The file format is not changing. So if anything ever breaks on that interface, you can just reopen the same notebook, even without restarting the kernel. You can say, okay, close that window, open that same notebook on the old interface and keep working. And then eventually, hopefully by next summer, we'll have reached 1.0 complete feature parity. Everything works robustly. We can basically deprecate the old interface and gradually phase it out. And hopefully, not only will this give us a better experience, but basically take this idea of these abstractions that we've understood over the last few years are really useful and make them now truly kind of the Lego blocks that I started with for others to build upon in an environment where new tools. So to give you one example that is relevant to this room before we close, in the summer, when we first announced this at the SciPy conference, in an afternoon, a couple of astronomers built a FITS viewer to add as a plugin to this. So because the architecture is designed for extension with plugins, it only took them a little bit of time to grab their existing FITS viewing code and add a little JupyterLab plugin so that you could bring up FITS images in this environment. So I'd like to thank you all. We have a couple of minutes for questions, but thanks for your attention. If there are any questions, I'd be happy to take them. So I'll repeat the question for the benefit of the webcasting audience. How do I see the balance between outreach and vision on the big things and kind of day-to-day engagement on the more basic things? It's always a tough question. We do run at the conferences tutorials and activities to teach how to use the basic system. So for example, at the last SciPy conference and at various conferences, we've run tutorials of this kind. We have been working quite a bit on documentation for the basic system. That we know that this has been a weakness of the project, partly because the project kind of exploded in complexity all over the map, and we lost control of that complexity. But we have been investing. Carol Willing, who's one of our software engineers on the project, who has a lot of experience on these questions, has already made really good inroads in improving the documentation, which was really a known weakness. And we're also going to hire, we have some resources in our current grants to hire a dedicated tech writer. And so that contract is actually almost ready. It's been basically doing just the HR process of getting a contract ready. And we're about to post that. So if anyone here is interested in the tech writing question or knows good tech writers who may be interested in working with this, please keep an ear out, and literally within the next week or two or the next few weeks that posting should be out. But it is true that even though we do have resources and funding, we are stretched actually quite thin. I mean, we are trying to do a lot. This is a really ambitious program, and the people in the core team who are fully funded to work on it are responsible and are beholden kind of to our funders for advancing the project in new ways. So I don't have a perfect answer. One thing we are going to do is maybe try to record a few. I have a new postdoc who's very interested in recording good short web videos and streaming videos that may serve some of this role. And one thing that I forgot to announce, but that I should mention, we don't have an exact date, but we will be hosting the first annual Jupyter conference next year. It's going to be, for those of you here, it's going to be very conveniently located just up the road in New York. So you don't have to get on a plane. You can get on civilized transportation like trains and make your way up there. It should be sometime in the summer of next year. And there, I think, will be a very good opportunity for doing a lot of actual outreach and training and building that capacity better. Yes, Sunny?
So does JupyterLab run on your servers, or can it run anywhere?
Oh, JupyterLab is basically the same thing that today you type Jupyter Notebook, you will type JupyterLab. So that one can run, it can run locally on your laptop, on localhost. It's just the new updated version of the notebook environment, which means this one will run. So this is what it looks like. This is what JupyterLab looks like, and I can type. Okay, let me. was a dead kernel. So I can type code here. I have my terminal down here. I can have a text editor here. This is running on localhost, just like my normal notebook. And it's basically just an updated version of that interface that simply gives me kind of this environment where I can have all of my tools in one place. That doesn't change. The thing that is really a server-side tool is Jupyter Hub. Jupyter Hub provides and brings this into the multi-user context. It's the one that knows about multiple users, has the concept of user identity. That only runs on Unix-type environments, right? Because that really is meant for server deployment. So Jupyter Hub assumes that you're on a Unix box. It doesn't run currently on Windows. We don't really have plans to port it yet and resources for Windows. But this will run locally on a Windows laptop, on a Mac laptop, on a Linux machine, on a Docker container, wherever you want.
As it's become more and more popular, is security an issue that you have to spend a lot of time worrying about?
So the question is security an issue as this becomes more popular? Security, what do you mean? The internet is a very safe place from what I've heard. Everyone is really nice on the internet. We're all friends here. So it's a horrible problem. And it's a horrible problem because we have built effectively the worst thing imaginable, which is we built a JavaScript platform with connections, with an explicit protocol to connect to arbitrary code execution, right? It's sort of the thing that anyone who thinks about security would say, never ever get within 1,000,000 miles of that idea. We said, that's where we're going to build a house, right? That's exactly what we're going to do. So yes, we've basically gone completely off the deep end in that regard, and we live happily there in that hell. Satan has a really, really good bar service, and we do have a security mailing list. So if you're interested in security, we have a security dedicated mailing list. We have private repositories that are shadow copies of our main repos, where if we have to develop a patch, we review it in private. And then we can make the release and get CVEs and whatnot for the releases without completely disclosing what the problem was, or at least the inner workings of the problem until the fixes have had a chance to propagate, hopefully. We've had people from industry who participate in that who have discovered security problems. IBM has done some spectacular work in basically uncovering security vulnerabilities in the framework and improving them. The fact that this is being deployed at supercomputing centers across the nation obviously means those people are looking at it. So yeah, we try to take it very seriously. It's not our domain of expertise, but we do have enough people in the team that this at least gets looked at seriously. But I'm not claiming that it's perfect, and I know, as I said, we're doing something truly horrible. And so buyer beware. I think there was a question here and then back here.
Yeah, so earlier you said that there was a problem of collaborating on a Python notebook. So what's like the best way right now to actually for two people to work on the same one, and in the future where do you see like collaboration?
So right now, in the official Jupyter Lab instance, there isn't, or in the Jupyter Notebook, there isn't any support for real-time collaboration. We are working on it. There's a hosted version of this by a company called SageMath Cloud that actually offers synchronization of the document itself. So on a SageMath Cloud server, and there's free accounts and there's for pay accounts from there. I have no connect. They were not on my slide because I have no commercial kind of connection with them, but I just know that I know them and I know that they host that. We are actually working on supporting that at the level of our protocol. So I have a new postdoc who just started 2 weeks ago at Berkeley. His paperwork just finished, who will focus on that problem of adding, and it's tricky, right? It's tricky because it's not just about the UI aspects of document synchronization, it's about the fact that we have this kernel side state. Who owns that? How does it get synchronized? Who has access to that side of the picture? It's not a trivial problem, but we are working on it. The SageMath Cloud solution is one avenue for that, and it kind of makes its own set of decisions on who and how the state is owned in the collaboration sense, and we still haven't completely finalized our decisions on that, but we have people working on it, and it's available. I mean, all the work is being done in the open source project, so if you're interested, you're welcome to join. There was a question back there.
The multi-language support is great. I've used it a couple times. Is there any thought to going like multiple kernels in the same notebook, similar to like what Beaker does?
So the question is whether there's any plans of going to multiple kernels in the same notebook at the same time. So I have a two-level answer to that question. The first one is, The IPython kernel has a flavor of that in the sense that IPython understands the concept of cell magics, right? And so in IPython, you can type $Ruby and that works because these cell magics allow you to declare this cell is something else. And we have cell magics for Fortran, Python, R, Julia, all the scripting languages. And some of them know how to exchange data back and forth. So for example, the Julia and the R kernels know how to share data with the underlying Python kernel. So this is a case where the IPython kernel is still, the notebook talks to just the IPython kernel, but the IPython kernel is capable of managing multiple other processes on the side. And for some of those connections, do pairwise data brokering, not for all of them. Now, the notion of saying one notebook has a collection of kernels simultaneously open is a line we haven't crossed. We are thinking about it. I think there may be valid use cases for doing it. It does introduce a fair amount of complexity for certain things, and so we're not completely sure what the right trade-off is there, but there are some solutions for that, and we are thinking about what would be the right user interface and the right user experience for when that is really needed without adding unnecessary complexity for the majority of cases, which are just single kernel. Because it does add actually, in the back, it adds a lot of complexity in the back.
Yeah, I can tell from how difficult it is to install and set up the Beaker notebook versus the Jupyter notebook. It's far simpler. But yeah, there's literally a handful of cases where you really want it, but it is a very cool feature of being able to do that.
Yeah, so I keep thinking about that one, and we keep kind of iterating on a few ideas, and so we may be able. This has the development and the building of all this interface has really taken a huge amount of kind of focus and resources to get this off the ground. But I think once this begins to stabilize, we can kind of open our brains again to thinking about some of these new questions. Thank you. No, but it's a very good and valid question. Perry, you had a question?
Yeah, a few years ago, Greg Wilson bemoaned the lack of a good diff for notebooks. Has that been solved?
So there's a project called NBDime, which is being developed. Oh, the question, by the way, was for the webcast audience was Greg Wilson a few years ago at a conference bemoaned the lack of good diffing tools for notebooks and version control support. And so there's a project now that is being developed by a postdoc at Simula who's working with Min Reagan Kelly, who is still funded by the project through Berkeley, but is now a postdoc at Simula himself. And so this fellow Martin, I'm blanking on Martin's last name right now, has been working on NBDime, short for Notebook Diff and Merge, which is exactly a collection of tools to help with diffing and merging the notebook as understanding the structure of the data rather than giving you the rather useless dump of the JSON diff, which is basically kind of like language, the compiler spilled its guts kind of situation. So I actually haven't had time to use NBDime extensively yet, but it is being actively developed, and I would point you and suggest that this would be the right place to kind of suggest, improve, criticize, etc. I don't know if do we have time for one more?
Oh, sure.
Please?
So some people note there's a bit of a tension between using a notebook as a lab notebook and as a presentation.
And as
As a presentation.
yes.
Where you talk to other people. So in one, the focus should be, ease of input, flexibility of input, fidelity of history, where you can't, where it's not so easy. You're usually not going back and changing things. But when you're doing it as a presentation, you want the output to be extremely pretty. You want, you're always going back and reshaping how you tell things. And these pull in slightly different directions. They sort of demand different features. Is this something that you think about a lot?
So yeah, the question is there's some tension between using a notebook as an ongoing record of the live exploration process of the scientist versus a presentation mode where you want to basically shape the narrative to tell something that kind of nice and clean with a specific organization, also with attention to kind of visual layout. You can see that I didn't use the notebook to make the presentation. I used Keynote just because it's easier to copy and paste figures and put them in the right place and resize and whatnot. That level of convenience, unfortunately, when you're writing your talks at 3 in the morning always helps. But there are tools. Yes, it is a tricky tension. It's something for which we don't have a perfect answer, but there are tools for that. So for example, Continuum has developed a tool called NB Present that actually allows you to take a notebook and turn it into a presentation, selectively choosing what goes in there, so that at least if it's a subset of what you do have in the notebook, you can expose it. And it does so by taking advantage of the fact that the notebook, as I mentioned, is a data structure with metadata attached to it. So in the metadata fields, you can record where this is supposed to go when being presented. Those are the same tools that IBM uses for this dashboard view that I talked about, where you can take a notebook. So this is a notebook, a normal notebook down here with code and whatnot. And if I go and click on this icon, I'm now looking at the same notebook, but now the code is gone. I haven't run it yet, so the figures are not loaded. I don't want to take the time to do it. But now all the code is gone, and all the things that were kind of intermediate are gone. And what's left are the plots and the results, still available for interaction, but now presented basically as a web dashboard. So those ideas of taking the document, annotating the metadata to produce a different output, I think give us some solutions for that, but it doesn't mean they're the perfect answer, and I think there's still kind of room for improvement on this.
Yeah, so I think it was disappointing that you didn't give the presentation out of a notebook.
I used to give my talks out of notebooks, but honestly, it really was down to the problem of like copy pasting things and moving them around visually and putting things here and there. It was just a matter of it's time consuming to do that when all you have to do is basically hand annotated markup in Markdown or HTML. It's just a little bit too much work, and I got lazy and too little sleep, and so yes, I'm a terrible person. What can I say?
Well, a very long time ago, Andrew Moore gave a presentation in this very auditorium, and he gave his entire presentation out of Emacs. Everybody was here for that.
You can't do that. Now, I should say that if I am giving a presentation that is very kind of code and data intensive, then I do use a notebook, because if the emphasis is less on kind of the big picture and kind of lots of screenshots and whatnot, but really let's look at this problem and this code and this data and let's change a parameter, then I do, and often what I'll have is some regular slides next to a notebook that focuses on that.
So I just want to let everybody know that there is a reception outside, so you can chat with Fernando for a little while longer, ask some questions.
Thanks, everyone.